Okay, so now we're ready to capture, not capture, that's what I'm doing a screen capture. We're ready to write our code here. So actually there's not a lot of code that we're going to have to write here, but we are going to look at this and do some debugging on here. So first off, let's think about the variables we need to have here. So remember, we need to have a 16-bit integer to get the number of counts. So I'm going to do ADC count. I'm going to initialize that to 0. We need a float number to store the volts in. Whoops, volts. And I'm going to set that equal to 0. And then we actually need one more, an unsigned int 8. And this is going to be PWM CMP, because that's my PWM compare value that I'm going to be writing in. And I'll start that at 0 as well. Then of course we have our enable global interrupts. So I might just say comment here, needed variables. The names are kind of self-explanatory. So place your initialization code here. So we have PWM clock. What did I call this? Oh, I didn't rename my clock here. What did I call my clock? I just left it as clock. Well, that wasn't necessarily the wisest thing to do, but it's clock underscore 1. Need to start up the clock. Okay, so the clock started up. And I'll say this is starting the PWM clock. Then I need to start my PWM. So start the PWM. And then remember, it's not necessary to put the extra spaces in here. What did I call this? Oh, I didn't rename this. I'm going to go back and rename this here and recompile this. I want to call this A analog to digital conversion of the pot. So I'm going to do that, and then I'm going to quickly rebuild my APIs. I could have changed the clock there at that point as well, but it's fine. So I need to start this. And then remember, we need to start performing conversions as well. This doesn't start performing conversions, that just initializes everything. So I need to do start convert, because then that's going to do it in conversions. And remember, we're in free running mode, so this starts the A to C, and then this starts the conversion. It is in free running mode, so this only needs to be called once. If you weren't in free running mode, you'd have to call that every single time you were going to take a measurement. You'd have to first do the conversion, then take the measurement. Now this is where I'm going to go here, my application, because I want this to run forever. And so I first need to get the number of counts, so ADC count, and this is going to be ADC pot. Remember, we looked on the data sheet in the previous video. This is going to be get result 16, and then we have to enter the channel. We only have one channel, and so it's just channel 0. Now if you had multiple channels that you were doing, it would be wise to make macros for those channels. So again, you don't have to remember, well, what channel is this particular analog signal on? Is it on 0, 1, 2, or 3? You would definitely want to do macros to make it so, this could be, you could call this like, pot channel, or, pot chan, or something like that, to make sure if you had multiple channels of analog to digital conversion so you wouldn't mess them up. But that's not necessary for this. Then what did we say we're going to do? Well, we need to convert this to a voltage. So I'm going to do volts is equal to A to C pot counts to volts. And then remember, it needs a channel, and then it needs the count. And then that's going to give me a voltage somewhere between 0 and 3.3 volts. And now I need to convert that back to an unsigned integer 18. And the way you're going to do this here is, well, first you're just going to do it's volts divided by 3.3 and then times 255. Because if you're at 3.3 volts, you divide that by 3.3, which is 1. And remember, our period for our PWM is 255, so you'd multiply that by 255. And clearly, if volts is 0, the PWM compare value is going to be set to 0. Now, one thing you should really do here, the reason I put this in parentheses is we should do this computation, but then we should, just for good coding practice, you should cast this, because this right here, this computation is a floating point computation, but we're wanting to have that floating point computation stored in an 8-bit integer. And so I'm casting it here. So I'm saying do this doing floating point, then convert it to an 8-bit integer, unsigned. And then the last thing we need to do is just write that value to the PWM. And then that's it. That's all our code that we need. Because what have we done here? Well, again, we started up the analog to digital conversion. We first got the result, converted it to volts, took that voltage and converted it back to this 255 here. Now, we can talk about it. Technically, we don't have to convert it to volts. We could have converted right from the ADC right to this PWM compare, but I wanted us to convert this to volts to see how we do that. And we will show this in the debug mode. So my video already shows that this works online, but I'm going to go ahead and put this in debug mode. See, isn't that so nice how fast it, compiled everything? So that was so nice. All right, so I'm going to put some breakpoints here. I'm going to put a breakpoint right there. So I'm going to forward my program all the way down here, and I'm going to look at some of the locals that we have here, some of the variables, and I'm going to step over and do one of these things. Now, A to DC count, it's 0x39A. That's hexadecimal. Well, you can change that on the default here. You can put it in octal, which is even a weirder format. You can put it in binary, because remember, it's a 16-bit integer. Or what's really nice is you can put it in decimal. So that count currently is 922. We'll step over again. It converts that to now 1.485659 volts is what that's computing it at. And we'll step down one more. And it computes this to 0x72. And I'm going to go ahead and read this as a decimal. So it's 114. And it's saying this is an unsigned character type, which is weird. I don't know why it's saying that, because it's definitely an unsigned integer. But it's at 114. And so that's what it would be writing in the PWM is 114. Now I'm going to move my pot. I moved it all the way to one side here. So we're then going to go back here. And now I'm reading 2047. Now if we look for a second, well, we can think about why it's giving me 2047 in a second here. I'm going to step over that again and get my voltage, 3.298 volts, which is essentially 3.3. And notice that you're getting 254, which basically is the 255, that we want. So technically, this pop, because I turned it all the way, doesn't actually get me all the way to 3.3 volts. I'm not actually ever getting exactly 255, but 254 out of 255, pretty darn close. All right, so now I'm going to turn it all the way the other direction. And now A to C count is -2. We convert that to a voltage, negative 0.000322. And so you're saying, well, that doesn't make sense. How can you get negative voltage? Remember, this is an analog to digital conversion. This is essentially 0 volts, right? So we step over. And notice then you get a 0 here, because by saying it's an unsigned int and doing this computation and casting it as an unsigned int, we're basically guaranteeing ourselves if it got a negative number, it's going to set that at 0 for us. So now I'm just going to go ahead and twist it a tiny bit. We'll do one more here. 224.369. And then that's 27. And so if you have this with a potentiometer, and again, you can just find a breadboard and a potentiometer and 211 in the lab and wire it up, and you should see the LED dimming and going on. So I'm going to take this breakpoint out, because if you're debugging like this, it's not going to look like it's dimming or doing anything like that. But if you let it just run continuously, then you will get the dimming effect on it. So neat little thing on how to do analog to digital conversion, because there is always lots of signals that are still out there that are analog signals, but you want to read them into a digital device. So this is how you would read those into the PSOC device. Oh, the one other thing I wanted to point out to you. See, this is a 12-bit SAR. So I'm going to pull up calculator here. Let's do 2 to the 12th power, 4096. So then if I divide that by 2, 2048. So see, when we got 2047, it's because we're using a 12-bit SAR here. And you might say, well, why is I only getting 11 bits? Well, that 12th bit is a signed bit for us. So we really only have 11 bits. So I really should have not done 2 to the 12th. I should have done 2, not squared, 2 to the 11th, because that 12th bit is a signed bit. And then they get 2048, which of course we know then we'd go 0 to 2047. And remember, we had that on that one. All right, so on Monday we're going to have an assignment where you're going to have to do this. And just to kind of give you an indication ahead of time, if you want to start working on it, this assignment's going to be kind of pulling everything together on this. You're going to basically use the potentiometer to set the brightness for the red, green, and blue, but then you're going to have to use the switch to switch between which LED you're controlling. So you're going to have one potentiometer. Actually, maybe we're not going to do one potentiometer. Maybe we'll do 3 potentiometers. I like that idea. 3 potentiometers, and then what we'll have to do is you will have 3 analog inputs, and one will control red, one will control green, and one will control blue. And so we'll be able to, have an RGB to be able to control it. And actually, that's something, it would have to be more sophisticated than what I'm describing here, but that's something you could do for a senior project. All right.